Dear students, as I told you in the last class, if heteroskedasticity is detected, we have to take steps to correct it. That is, we have to consider the remedies. Now, as far as remedies are concerned, there are two approaches. We know that if there is heteroskedasticity, expected ui square is sigma square I. So, we consider the remedies to heteroskedasticity on the assumption that heteroskedasticity pattern is known, and also on the assumption that it is unknown. Now, first we consider the case in which heteroskedasticity pattern is unknown. We assume that our model is yi is equal to beta 1 plus beta 2 xi plus ui, a simple two-variable model. We initially assume that sigma square I is known. And if sigma square I is known, the method of correction is known as weighted least squares, WLS. Actually, it is a case, it is nothing but a special case of GLS. We will use the terms interchangeably. GLS is same as WLS, that I will explain later. Now, if sigma square I is known, the solution to heteroskedasticity is divide the model throughout with sigma I. Yi by sigma I is equal to beta 1 into 1 by sigma I plus beta 2 xi by sigma I plus ui by sigma I. Divided throughout with sigma I. Now, this is the new model. So, in the new model, you consider the variance of ui by sigma I. This is equal to sigma square I, what variance of the first quantity is 1 by sigma square, that is 1 by sigma square I into variance of ui is sigma square I is equal to 1. So, if you divide this model throughout with a sigma I, you know that in the new model, the variance is a constant. That is, the new model satisfies all the classical assumptions. So, if you apply OLS to estimate beta 1 and beta 2, you have the estimators which are blue. Now, while discussing autocorrelation and heteroskedasticity together as non-spherical disturbances, we have stated that in the model y is equal to x beta plus u, and if expected u transpose is equal to sigma square psi, the method of correcting this heteroskedasticity is transform the model in such a way that in the transformed model, the error term satisfies all the classical assumptions. We have suggested in matrix form to pre-multiply the model with the P is equal to Px beta plus P. In this model, the new disturbance is Pu, and as we have stated earlier, expected Pu transpose is equal to sigma square I. You just refresh, just to go back. So, applying OLS to the transformed model is GLS. If you apply OLS here, you will get estimators which are not efficient. If you apply OLS here, you will get estimators which are blue. So, the process by which the original model is transformed in such a way that in the transformed model OLS, U satisfy all the classical assumptions is GLS. GLS is OLS applied to the transformed model. While discussing this topic, I mentioned that I will explain PU later. Now, what is this PU matrix? U, we know that is nothing but U1, U2, etc., Un. So, P into U produce what is known as Ui by sigma I. So, consider 1 by sigma I, 0, 0, 1 by sigma I, 0, 0, 0, 1 by sigma I. Now, if you multiply this U1 by sigma 1, 1 by sigma 1, as we explain it in terms of sigma 2, sigma n, ui by sigma I, u1 by sigma 1, then u2 by sigma 2, etc., un by sigma n. So, this is the P matrix here. 1 by sigma 1, 1 by sigma 2, 1 by sigma n. The off diagonal terms are zeros. Diagonal elements are given. Pre-multiply this, you will get it. So, what is Py? Y1 by sigma 1, y2 by sigma 2, y3, etc., etc. You can create all these variables. You will get estimators. We treat it as beta star 1 and beta star 2 because these are different from beta hat 1 and beta 2 hat. They are OLS, these are GLS. So, if the pattern of heteroskedasticity is known to us, the solution is very easy. But in most cases, we will not know the pattern of heteroskedasticity. Now, the question is, if the pattern of heteroskedasticity is not known, what is the solution? Now, if the pattern of heteroskedasticity is unknown, we will make a plausible assumptions about the heteroskedasticity pattern. We will make plausible assumptions about heteroskedasticity pattern. Let us consider a few cases. We assume that expected ui square is equal to sigma square xi square. That is, we assume that in the model, error variance is proportional to the square of x. Error variance is proportional to sigma square I xi proportional to the square of x. The pattern is like this. Error variance is proportional to the square of x. Now, if we assume that error variance is proportional to the square of x in the spirit of Park test or Gletser test or the graphical method, then the solution is divide throughout with the xi. yi by xi is equal to beta 1 into 1 by xi plus beta 2 plus ui by xi. Ui by xi. Now, what is expected value of or the variance of ui by xi? Is equal to 1 by xi square into what is variance of ui? Sigma square into xi square is equal to sigma square. Sigma square. So, if we assume that error variance is proportional to the square of x, the solution is divide the model throughout with the xi. That will produce what is known as GLS. This is also a GLS procedure because here also the originalist model is transformed in such a way that the disturbance in the transformed model satisfy all the classical assumptions. But if you compare this with this, you will see that in the original model, beta 1 is the intercept, but in the new model, it is the slope. beta 2 in the original model is slope, in the new model it is intercept. But this is not a problem. We will obtain beta 1 and beta 2. And if you want to get the original model, multiply throughout with the xi. So this is the solution if sigma square is assumed to be sigma square xi square divided throughout with the xi. Now suppose that we assume that the error variance is proportional to xi. That is expected ui square is sigma square xi. In the model, expected ui square is sigma square xi. Then the solution is divided throughout with the root xi. That is yi by root xi is equal to beta 1 into 1 by root xi plus beta 2 xi by root xi plus ui by root xi. And can also be written as beta 1 into 1 by root xi plus beta 2 xi by root xi is root xi plus ui by root xi. Now consider this disturbance. Variance of ui by root xi is equal to 1 by root xi square, that is 1 by xi into sigma square xi. Again it is sigma square. So if error variance is assumed to be proportional to xi divided throughout with the root xi, that is the solution. That is, if the pattern is something like this, sigma square I, when you plot it, the pattern is like this. Note the square of xi is proportional to xi. If it is square, it increases non-linearly. If it is proportional to xi, it increases linearly, like this. Now here, in this model, what is the P matrix? The P matrix here is, this is U1, U2, etc., Un. The P matrix here is 1 by x1, all the other values are 0, 0, 1 by x2, zeros, 0, 1 by xn, because u1 by x1, u2 by x2, u2 by, un by xn. Similarly, all the other values are changed likewise. So this is a solution. Now we assume that error variance is proportional to the square of the mean value of y. Error variance is proportional to the square value of the mean of y. That is, we assume that expected ui square is sigma square of expected y I, this expect is proportional to the square of expected y, the square of expected y. If this is the pattern which we assume, then divide yi is equal to beta 1 plus beta 2 xi plus ui. Divide throughout with the expected yi. Yi by expected yi is equal to beta 1 into 1 by expected yi plus beta 2 xi by expected yi plus ui by expected yi. Now variance of ui by expected yi is equal to 1 by expected yi square into sigma square into expected yi square is equal to sigma square. So if we assume that it is the square proportional to the square of expected y, then divide throughout with the expected y. And since expected y is equal to beta 1 plus beta 2 xi, we can use instead beta 1 plus. Now the problem here is expected y is unknown. Expected y is the conditional mean value, the population regression function is unknown. So what we do here is we estimate the model, obtain y hat I, and we use y hat I as a proxy for expected y. So to implement this, we divide yi by y hat I is equal to beta 1 into 1 by y hat I plus beta 2 xi by y hat I plus ui by y hat I. To implement this is the procedure which we use. We estimate this model assuming that there is no heteroskedasticity. Then we obtain the estimated values of expected y, that is y hat, and y hat is used to transform the model. Now remember this, in all these we have expected y ui square, that is sigma square I. Expected ui square has a particular form, that is sigma square into a function of x. Then the solution is divide the model with the root of this fx. If it is sigma square x square, divide with the x, that is root of x square. If it is sigma square x, divide with the root of x, like that. So if expected ui square is sigma square I, then that is equal to sigma square of x. The solution is divide the model throughout with the fx. Then there is one more solution. Suppose that this is our original model, and suppose also that we give a log transformation. Ln y is equal beta 1 plus beta 2 ln xi plus ui. Suppose the model is specified in log form. If you re-specify a model in log form, it reduces heteroskedasticity considerably. The reason is log transformation compresses the scales in which x and y are measured. It compresses the scales in which dependent and independent variables are measured. For example, a log transformation reduces tenfold difference between two values into tenfold difference into twofold difference. Log transformation compresses tenfold difference into twofold difference. For example, consider 8 and 80. 80 is 10 times 8. But if you take ln 80, it is equal to 4.32. And ln 80 is equal to 2.07. Heteroskedasticity pattern is like this. So if as the value of x increases, and if the model is specified in log terms, it compresses the high-end values considerably, because ln 80 is 4 only, ln 80 is 2. So tenfold difference is compressed into a twofold difference. So if you are using a cross-section data, and if you observe that heteroskedasticity is a problem, you convert the variables into log form. But log conversion is possible if and only if your variable has only positive values. Keep it all mind. Keep it always in your mind. Also, log transformation is not possible for all the variables. Giving a log transformation to the age of a person is not a good procedure. Log transformation, if and only if it is an economic variable like consumption, income, GDP, etc. Anyway, if a log transformation is possible, then in some cases heteroscedasticity problem may be solved. My point is this: if in your original model heteroscedasticity is a problem, give a log transformation and see whether the problem of heteroscedasticity is solved or not. If it is solved, you can continue with the model. So these are all solutions if and only if you can assume that the heteroscedasticity pattern is known. But the problem is, in most cases, heteroscedasticity pattern is unknown. If it is unknown, and solution will be difficult in this way. So in the next class, we will discuss what the researchers actually do to solve the problem of heteroskedasticity.